Hi. So at this point of our treatment on chapter 6 and semiconductors, we have now understood how we can calculate how many carriers we have either in the conduction band, so how many electrons we have in a conduction band, or how many hole states we have in the valence band. So what are the carrier concentrations? And we have understood that we can really affect these carrier concentrations by doping of our semiconductor. And now we are ready to go to the section 6.4, which allows us to estimate what is really the macroscopic electrical conductivity of a semiconductor. And here I will really divide this section into two different pieces. And first I will be considering the mobility of carriers. And in this lecture, I will want to kind of explain to you that what are the different contributions that really affect a semiconductor's electrical conductivity. So mainly I will be discussing with you or having a monologue with you how the conductivity of a semiconductor is really being defined as a sum of contributions from both types of carriers. So in essence, the electrical conductivity is both due to an effect of electrons moving at the conduction band and similarly holes moving at the valence band. And in this slide, I will also explain what are carrier mobilities and what affects their values. And as the name of this lecture suggests, like this is actually an important topic that really affects the kind of final values of electrical conductivities when we are considering different semiconductor materials. And finally, after this, we will go into the Hall effect, which allows us to estimate how we could actually measure experimentally these carrier concentrations in a piece of a semiconductor. But let's start with the mobility and elucidate how we can understand a macroscopic process of electrical conductivity in a piece of a semiconductor. And what happens in semiconductors in terms of the electrical conductivity is that really it is different from electrical conductivity of metals. So here we have a carrier concentration, and of course this is related to the electrical conductivity, and this carrier concentration really quite sensitively depends on the temperature of the system. So like I already in the previous lecture mentioned, the temperature dependence of electrical conductivity for a metal is such that the metals usually they conduct electricity worse when we increase the temperature, but the opposite is the case for a semiconductor. And this is due to the fact that we are changing quite dramatically the carrier concentrations when we are increasing the temperature of our semiconductor. And this does not happen with metals. So we do not really have that kind of temperature dependence on carrier concentrations. In both types of materials, the mobilities will be decreased for the carriers so that they do not move as easily through the solid anymore when we increase the temperature. But for the case of semiconductors, this process is negligible compared to the change in the carrier concentrations. And as a whole, we see this kind of different temperature dependence on electrical conductivities. Another thing that is different when we are considering the electrical conductivities of semiconductors is that we may have both carriers that can participate to the process of electrical conductivity. So we may have holes at the valence band that are propagating, and we may also have electrons at the conduction band that are propagating. And most of the time, we actually do have both, and they can both readily participate to the process of electrical flow. Of course, we can consider metals, and usually for the case of metals, we assume, or this is actually quite true, most of the time for metals, the conductivity is due to conduction electrons. So most of the time for metals, we do not need to consider holes at all. But there are some counter examples, and aluminum, for example, is a counter example of an elemental metal that in fact the conductivity is mostly due to holes. So that's a kind of like a good counter example of this. But nevertheless, it's a good rule of thumb. For metals, it's really the conduction electrons that give rise to electrical conductivity. And now, since we do have electrons and we do have holes in a semiconductor, what we must do in our treatment is that we should really consider both carriers, and we must take them properly into account in the calculation. So we need to modify our current approach to calculate the conductivities of such materials. And this is what we will be doing here in this lecture. So let's now introduce a quantity known as a mobility, and mobility mu is defined as a velocity, or the modulus of velocity of these carriers, divided by E, and E is the applied static electric field. So in essence, this could be described using a potential difference. If you're more familiar with voltages and potential differences when we are thinking of a piece of a metal wire or a semiconductor, so that of course, field can be described as a electrostatic potential. So V is the carrier drift velocity, and we take the modulus, and then we divide that with the applied field, electric field's strength, and this is what gives us the mobility. So in a way, mobility is a quantity that tells us how easily the carriers will be moved when they are in an applied electric field. And now, since we may have both types of carriers, the total conductivity sigma can actually be there now written as a kind of summation. So sigma, total conductivity, is now the summation of carrier concentrations of electrons at the conduction band times their charge times their electron mobility plus a contribution from holes at the valence band. So we take the hole concentration at the valence band times their charge times their mobility, so mu h. So N is the electron concentration at the conduction band, and P is the hole concentration at the valence band. And E, of course, is the electric charge. And these mobilities, mu E's and mu H's, they are the electron and hole mobilities, respectively. And please note in this equation that we have symmetry with respect to the both types of carriers. So in a way, both can equally well participate in the macroscopic formation of current. The only thing what is different is that, of course, their concentrations might be different and their mobilities might be different, but at least mathematics-wise, their contributions are symmetric. And now let's look just a kind of qualitative level, how these mobilities could be described, and subsequently what are the things that on a microscopic scale in our material could affect the carrier mobilities. So let's start by noting that the carrier mobilities muse how electrons or holes are moving through our piece of a solid. Of course, the overall process is a stochastic in nature, so we should really consider statistics of process. So it's not just enough to consider a single electron moving, but we should actually consider a mass of electrons moving, and then these parameters that we are using, they should be stochastic in nature. So they describe how electrons or how holes behave on average when they are moving inside our piece of a semiconductor. And the kind of processes that happen, of course, the electrons and holes, their movement can be affected by scattering processes. And as we remember from earlier treatments, these kind of scattering processes can be effectively described by introducing relaxation times as parameters, so taus in essence. Another thing, what matters for a movement of a particle, of course, it will be its mass. And now, since we are dealing with collective excitations, so we have these electrons and holes, they are in essence affected by the electronic band structure of our solid. So instead of normal free space electrons mass, we should consider the effective masses associated with the electrons on these given bands. So all in all, what we have is that we can write the electron mobility, mu E, as a form simply that is the electric charge times the relaxation time associated with the electronic state at the conduction band divided with the effective mass of this state. And then similarly, we have an equal relation for the whole mobilities, so mu h, and we have E times relaxation time of the whole state divided by its effective mass. So this is the kind of simple relation that we have for the mobilities. And here, please note that the kind of longer the relaxation time, of course, the higher the mobility can be. And the smaller the effective mass is, the higher the mobility can be. And of course, this makes sense. Like if this relaxation time gives us roughly the time window during which our state can propagate without being scattering with anything nearby. So without scattering with other electrons, or without being scattering with defects, or without being scattering with the kind of like atomic lattice, so that the kind of higher the relaxation time, the higher the mobility will be. And subsequently, looking at this equation, we see that if we would want to, or we would need to change the property of our material, we would see that what we should try to do in order to increase the mobility. So for example, decrease the number of defects in our system, and for example, decreasing the temperature in principle would at least increase this. But on the other hand, that might not be a good approach with semiconductors, because then the carrier concentrations dramatically get reduced. And of course, depending on the band structure, the effective masses will be modified. So these are the kind of things that we can see quite easily by just looking at these kind of simple equations. And that's of course nice when we are able to have something like analytically solvable and understandable, because then we can get good insights based on simple mathematics. For simplicity, let's just assume that we have the relaxation time of an electron equal or almost equal to the relaxation time of our whole state. And let's note that usually it's actually the effective mass of an electron that is being smaller than the effective mass of a hole. This is related to the band structure, so that usually the band curvature of a valence band is not as strong, it's not as tightly curved as the conduction band, and this gives rise to this trend that we have with the effective masses. So in essence, these together imply that higher conductivity would be achieved by N-type doping of the semiconductor. And this is mostly due to the fact that if the relaxation times are roughly the same, but if there's on average a change in the effective masses such that the electron states have smaller effective masses, then it's beneficial to N-dope your semiconductor if you just want to maximize the conductivity of the semiconductor. So I've said this many times already, the band structure is important, but I hope this also clarifies this point, that when we are doing solid state physics, like a band structure is usually the kind of starting point for about everything. And please recall that in terms of semiconductor industry and semiconductor physics, we are, in essence, most of the time when we are talking with engineers, we are interested in semiconductor components. And when we want to make electrical components, semiconductor components, we need both P-type doped semiconductor regions, and then we need N-type doped semiconductor regions, so that we can form junctions, so that we can form P-N junctions, and then subsequently we can form more complicated P-N-P junctions, so that we could make transistors. So in essence, when we want to make electrical circuits where we have components such as diodes, transistors, light-emitting diodes, or light-absorbing diodes, or photodiodes, and such, then is that when it becomes of utmost importance to dope your semiconductor regions with different types. But these considerations I leave for other courses and other lectures. That this is not our main focus on a course on solid-state physics. So thanks for listening this lecture, and please join me soon with the final lecture we have on chapter 6 that will be uncovering to you what is a Hall effect and what is its importance in terms of semiconductors. So thanks and bye-bye.